In today's video, we're going to be looking at electromagnetic radiation. First, consider three different ways that you might interact with electromagnetic radiation. First, you might be exposed to energy from the sun. Maybe you go to the doctor's office and get an X-ray, and perhaps on the way there you're listening to music from your favorite radio station. All three of those are examples of kinds of electromagnetic radiation. Even though we interact with them in very different ways, they have very different energies and potentially very different dangers. All three are related to one another. Let's study them in a little bit more detail. All electromagnetic radiation consists of waves. It's just the properties of those waves are a little bit different, and those gives us the different kinds of radiation. The first property of a wave we care about is the distance between two troughs, or distance between two peaks, or really the distance between any two similar points on this wave. We call that the wavelength. And we use the Greek lowercase letter lambda to represent the wavelength. The second property of a wave that we're concerned with is the speed of that wave. And it turns out that all electromagnetic radiation in a vacuum has the same speed, that is, the speed of light. So for our purposes, electromagnetic radiation will have a speed of 2.99 times 10 to the 8th meters per second. Here we're going to use the constant c to represent speed, as again, speed is a constant for radiation in a vacuum. Remember, 2.99 times 10 to the 8th meters per second, that's very fast. A third property of electromagnetic radiation is frequency. Frequency refers to how often a wave passes a given point, and we represent it with the variable f. Frequency is dependent upon two things. It's dependent upon speed, and it's dependent upon wavelength. The faster a wave travels, the higher the frequency would be. The shorter the wavelength, the higher the frequency. But remember, because speed is a constant, frequency for our purposes will only be dependent upon the wavelength. Longer wavelengths means fewer points pass per second. Shorter wavelengths means more points pass per second. We'll come back to that relationship in just a little bit. But one more thing to pay attention to now is frequency for units has units of times per second, 1/2, or hertz. And think about when you tune into a radio station, you might tune into 99.5 or 101.3. Those radio stations are megahertz. That gives you an idea of how many times that radio wave passes a given point, that is your receiver, every second. The final property of waves that we're concerned with right here is energy. Energy will represent with an E and measured in joules. To get an idea of how wavelength and frequency play into the energy of a wave, let's take a look at several different examples of electromagnetic radiation. Down here we see a chart showing radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Notice a couple of things. Gamma rays have an incredibly short wavelength and high frequency. That is, lots of waves pass a given point in a second. Radio and microwaves have much longer wavelengths and much lower frequencies. You can see this measured with the wavelength, where radio waves are on the order of 10 to the 3rd meters, gamma rays 10 to the minus 12th meters. Now, let's think about the kinds of radiation that we want to avoid, or is dangerous, versus the kinds of radiation that's not. Gamma rays, X-rays, and ultraviolet radiation, those you all want to avoid, or at least limit your exposure to. That's why we wear sunblock at the beach or cover ourselves up. That's why we sit underneath lead protection when going and getting an X-ray. Gamma rays, thankfully, we're protected from by the Earth's atmosphere and magnetosphere. Radio waves, microwaves, infrared, and visible, on the other hand, we're not so worried about that. So what we can see here then is there's a relationship, whereas the frequency of a wave increases, the energy of that wave also increases. Higher energy more dangerous. As the frequency of a wave goes down, the energy of that wave goes down. Lower frequency, less energy. Let's now take these different relationships and come up with two different equations that relate our variables. Consider frequency and wavelength. As the wavelength goes down, that is, as the waves get closer and closer together, the frequency would go up. If the wavelength gets longer, if we stretch that wave out, the frequency would go down. So what we see here is an inverse proportionality between those two terms, that wavelength is proportional to 1 over the frequency. However, we can't do math with a proportionality, so we need to insert a proportionality constant, in this case c, or the speed of light, to change our proportionality into an equality. We still have the same relationship here, where wavelength and frequency are inversely proportional, but now, because of the proportionality constant, we can do some math. Here is one equation to remember, again remembering that c is equal to the speed of light. The next equation I want to look at is the relationship between energy and frequency. Remember what we saw earlier? As frequency goes up, energy goes up, or if frequency goes down, energy goes down. This gives us a direct relationship between those two variables. Again, we can't do math with a proportionality, so we need to insert a proportionality constant. In this case, the proportionality constant is not the speed of light, but rather h, something known as Planck's constant. It's not super important what exactly this number means, but it is going to be valuable to use it. So we need to come up with a value of 6.63 times 10 to the minus 35 joules per second. Really, Planck's constant refers to the smallest possible increment that we can measure values in. Sound good? In conclusion, let's summarize what we've talked about so far. Here's our wave. It has a certain wavelength. That wavelength can be stretched or can be compressed. It has a certain frequency. That's the number of times a point passes, a wave passes a given point. It has an energy associated with it. One other thing I should mention about that energy, and I apologize for not saying it earlier, is the energy is actually the energy of a single photon of light in that wave. This is where light gets a little bit tricky. Remember that light can either be a wave or a particle. Talking about a wave, things such as frequency and wavelength make sense. Talking about a particle, we can envision the energy of an individual photon. I'm not worried too much about that relationship, but keep in mind that we talk about energy, we are again talking about the energy as if wave were a photon. So again, we have a wavelength, a frequency, and an energy of that wave. And remember, when you hear the term electromagnetic radiation, you might be talking about anything from the energy of the sun, to X-rays, to radio waves. Thanks for watching.